My name is Simon Muff from Keysight Technologies, and I want to guide you through the EMCO simulation techniques we offer from Keysight. And my job is business development, so I want to introduce you to what actually our customers are doing in terms of analysis in power electronic systems. And I'm not sure whether all of you, but very briefly, know Keysight. And this goes back to 1939, well, when Bill Hewlett and Dave Packard built the first oscillator for Disney Studios. And Keysight is basically, after some previous things in between, called Agilent, is now the original measurement and test equipment manufacturer where Hewlett Packard started with about 70 years ago. Yeah? So this is where we're coming from, and what I want to talk today about is basically the EEsoft part. This is the software simulation part of Keysight, and this we are also doing since approximately 40 years, so it's not new in the market. A lot of you might know Advanced Design System, and I want to talk about pre- and post-layout simulation to reduce EMC problems in the means of power electronic systems, and later on to guide you over to the afternoon where we have a 2-hour session on 5G and high-speed board design, a little bit then ending up with high-speed digital. The physical effects are basically the same. Here you see the agenda, and I just want to introduce you through the the flow of the presentation. When we talk about fast switching devices, then basically we have, of course, the high-speed part I will show later with USB, PCI, and so on. But what also becomes very, critical in terms of EMC are the new GaN and SiC systems in the market with, lower DIDT. Here you can see where you are going with, solar plants, with electrical vehicles. And basically the DIDT gets very high, introducing EMC problems. Let's say the customer demand here we see in the market is always the same. You want to lower cost, you want a smaller size, you want a higher power density, you want to have a faster switching. And of course, you do not get rid of your parasitics and your DIDT. And if you, let's say, basically think of, it's a switching frequency of some kilohertz, maybe 1 or 2 megahertz, that's not so much. And I have designed that for 20 years, and you should probably have a good guess what you do. But it could happen, as you can see here on the right side, that something is completely dimensioned wrong in the system. And this basically happens as you cannot think anymore in a classical signal path from A to B. You have to consider also the return path. And return path not necessarily means that this is for a certain frequency or it's DC given. So if you see here on the left side, the number of harmonics in a switching event, you can see you need up to 50 harmonics, that it reasonably looks like a rectangle. So, and if you have a pulse switching, at 1 or 2 megahertz, you introduce, and you see that in the spectrum on the right side, these fast GaN and SiC switching devices inject into the system, and harmonics up to maybe 1 gigahertz, 2 gigahertz. And let's say here the impedance is, or the discontinuity in your path determines what kind of, or what portion of that energy is going through and what portion of the energy is reflected. And a return path is not necessarily a solid ground plane it's the best you can have, this is clear. But in these power electronic systems, you often have 2-layer boards only or 4-layer board. It's highly cost sensitive. And so you have a lot of spares around these return currents. Yeah? And the high harmonics being injected, you see here on the upper a simulation of such a switching event without a layout, and here with a layout. And basically you see the conducted and radiated emission you introduce by such a switching event, and as already mentioned, you hear very fast in the gigahertz range. And depending on your specification, like CISPR, very famous for automotive, you basically end up with violating your later EMC test. And simulation here gives you basically the ability to evaluate switching circuits, inverters, buck converters, and all that kind of stuff. Here, another example, for instance, the layout implementation destroying your performance, basically. Here, this was I think it was a buck converter with an efficiency of 73%, and then simulated with the layout and efficiency drop about 20%. I mean, if you look to the waveforms themselves and the increased emissions, you can directly see there is somewhere in the path the inductivity killing you, basically. And I will show you later on a real example, what we have published as an IEEE paper on the last Power Electronics Conference at DAPE in Genua. And if you're interested, then I'm walking around later on, just contact me. You can exchange, and I can get you a hold on the paper. And basically, what happens here is often your design flow plans to have a respin, because you have a first prototype of the board, and you plan anyhow later on that you have a respin because you fix a lot of other stuff as well. But let's say if you are entering such design space with new devices, you might see effects you have not seen before. And then it's hard to stay in your schedule with the respin, despite the fact that you are several 10Ks you can easily spend and some weeks of delay. Whether you plan for or not plan for, I would really, let's say, this is what I'm talking about here, if you do a pre-layout simulation, and this is mainly SPICE-based, and there are free simulators on the market, you download the models, you're questioning the model accuracy, most likely not in a usual day, because it's the only thing you have. But in these application eras of high DIDT, you simply fail basically just by implementing one-on-one, and then your respin time may not, let's say, be sufficient to the error detection you have to run, yeah? And what really fixes your design in the end. And so simulation becomes more and more important when you're going to higher DIDTs, and often the DT is not the deciding factor. The power gets higher and higher, you can switch, and so the DI is the demanding factor. ADS, what we have here from ESA, from Keysight, offers you also here the possibility, very easy. We have a power electronics library, and basically I will go later on a little bit more on the models we have for high electron mobility transistors, for instance, and other power electronic parts which are very usual, like a gate driver, like a control mechanism for a pulse width modulated switch. And this kind of stuff you can easily implement here by drag and drop, and then you see here two gate drivers where you read in, for instance, a SPICE model, yeah, file, import, SPICE, and then add a symbol. And here you see the half bridge of the FETs itself, and I will show later on the modified HEMT model, high electron mobility transistor model we have implemented. And it allows you basically then to easy drag and drop these to the layout, and you see here on the red nets shown, you can directly then implement basically a layout. This is in this case what was done here for that easy half bridge, and you can see directly here things you can try here, for instance the capacitor position. Yeah, of course, the capacitor position you can change very easy in such studies. Yeah, in the beginning, it's pretty clear here shown. Then if you're going closer to the switching port, you close the loop. I will show it later in more detail. And so if your loop is smaller, your inductance is smaller AC-wise, and so you reduce the ringing. Yeah, that's basically. And you can also parameterize such positions. You can parameterize the value. You can run a design of experience or any other kind of batch simulation. And so, how to say, get a very early feeling of your design space. Yeah? Let's say here you can see another effect. There is a lag with power below and the ground. This is the red one. And the ground was not really pulled in that design. So this was a red-in design, for instance, from Altium. And let's say here adding a ground flood could really reduce the ringing significantly, because then the impedance basically of that port, or let's say offering a closer return path, having a smaller loop, changing the impedance for the high harmonics, then really helps you here to have a better switching event between the two legs here, basically. How do we do that? Very shortly, you can also start, for instance, with your layout you have already. You're going to a new product generation. You just exchange the FET models or the other SPICE models and take the layout from previously, even if you do not necessarily match the layout from the footprint and so on. But you could, if it's a 3-pin device, if it's a 4-pin device with a Kelvin pin, you can still easily test, would my layout I have done before still fulfill the specification. And so we read in here from Altium, for instance, a ODB++ container, and you have a GUI where you can easily, per drag and drop, set up the schematic. So this is not all, how to say, hand drawn. It's basically here generated from the layout simply by dragging the components you need or the nets you want to analyze to your analysis. And then you have a button to generate automatically, for instance, a CISPR 25 test bench, and automatically your ports you need for the extraction of the layout parasitics are defined in the schematic, and the connection is done automatically. The simulation is run, because the setups and CISPR are, how to say, pretty well known. Of course, you have to specify some things like switching frequency, then the current you want to draw, or the voltage you switch. But despite these facts, this is very, very fast, and you can have a conducted emission test. Of course, all these tests and the accuracy compared to measurements are, how to say, dependent on the accuracy of the device models you put in. And this is why we thought about here as a measurement company, and we have a so-called PD1000 system you see here. It's consisting of a curve tracer, it's consisting of a double pulse test system, and of course a VNA for the S parameter measurements. Let's say you are not necessarily bound here for that flow to use the Keysight test equipment. I mean, a lot of people developing power electronics systems or developing power electronic devices have for a very long time already these systems in place, and they have their own data, and you can easily convert them and then hand them over to, and this is the key thing here, that we have a modified mathematical model. So we have modified the Angelov model. I have several slides, but just one here and the next one to show some details. And we call it Power Electronics Model Generator. So you bring in your data and you generate a new SPICE model description. Yeah? You can use then in what I have shown previously, these kind of simulations, or of course in any other simulator. And this accuracy is really key here. Very shortly, this is I put in for reference. Who's interested in this? Was published in September 2018. Modified Angelov model for GAN or SiC transistors, and let's say we have added some, additional mathematical descriptions. You can see here in the circuit if you compare to the standard one, and basically it's all about the description of the gate charge, its source effects. This also, as man already said, with the GaN, the big advantage of a GaN transistor is that there is no charge recovery, and between the pins, and let's say this is why it is enabled for certain switching circuitry, where it really helps a lot in fast switching, and I think this will spread out pretty fast. If you then have such a model, you hear just one comparison between conventional, what would mean I take a model, a SPICE model offered for such a switching device from the vendor's web page, and download it, and let's say on the right side, then compared with the modified model, what we have built in here, and then you can really see that some curves are really then here really different, and let's say the noise is modeled much more correctly, and you see here a comparison of such a device between simulation and measurement, and that fits pretty well, especially in the low frequency era, of course. This helps a lot, and as said, the flow we have now here to offer is basically that you can really read that in, and by one mouse button you have a test bench which consists of the filters basically. So we have also libraries where you can have filters like from companies like Word, or you read in SPICE or S parameter models, and then the load and the power source is modeled in an automated test bench per mouse button basically, and the virtual EMI receiver and spectrum analyzer in ADS basically then gives you the possibility to show the conducted emission, the spectrum plot in 3 meters, in 10 meters. And on top of that, I'm not necessarily a friend of these pictures on the lower left, but if you not really understand what's going on, it's helpful if you plot the current density or the field distribution, and you can really see where you have, most likely they are plotted red, so we call it hotspots, but it's not hot in a way, but where you have field concentration or high current density or high magnetic fields, and it gives you an indication where the design can be relaxed, where you can do something. For instance here, this is such a power switching cord, and you see here the connections here between the 3 phases. They may be missing ground, maybe the traces are not wide enough, or the stack up is not, or can be optimized, and so you can find really where you have your improvement potentials in the board, and often basically it's spaced there in the layout, you just have not thought about that the most current is flowing this few millimeters, and you can ease it. So this is I think even an Altium picture. It's a case study. This is the one I mentioned, which was published in September. Just show you really live what customer did here on such a board. And of course, for these big caps and inductors, a lot of models have been, of course, to be added to the tool. I mean, if you want to start, you have done a model library. This is here, you reuse your parts. You can download from vendor pages. And this is a 3-phase Vienna rectifier for automotive application. And let's say first simulating that, you see here the phases 1 to 3, and that looks all pretty clean. And this is a simulation just by the circuitry. Ideal models, ideal circuitry, and no PCB parasitics. And looks all pretty clean, and you say, okay, that's what I want, fine. Next step was from the customer. This is a little bit of marketing view. You can also have the layout as a box here. This is clear, and connect to your circuitry is replacing all the filters and everything with respective models and S parameters and adding the PCB and connecting it. The load was here some ohms, I think 50. And basically with the extracted S parameter model, and this is the EMCO simulation, you run your time domain simulation and the excitations you have by that, you will give you the current distribution and the voltage distribution on your layout, and the feedback basically from the layout to your circuitry is included. Yeah? So you can see all the reflections traveling around, the losses and that kind of stuff. And what first came out, okay, I violate some max ringing ratings for the voltage. I have a ringing. Where does it come from? As said, there is a detailed paper published, referenced in the slide set you will get access to later on the conference. And so I go directly to the solution, and on the input side, basically it turned out, you see here, two lines, one to the bottom, one to the top. This is the ground, and here you have one phase and on the other phase. And sorry, let me see, too fast. And so it's pretty obvious if you look to the layout, they are different in length. The loops you drive the phase in. And from that perspective, just calculating the inductance you can do in a very easy simulation. You put a port and then you short to one end, and so you basically look at your impedance is omega L, and you calculate the inductance. And you could see, if you would think in such parasitic lumped values, I mean, there is no lumped inductance, it's always a loop, yeah? And the loop inductance gives you only, the magnetic flow. But it's very unsymmetrical. The one had, I think, when I have it correct in mind, 6 nanohenry something, and the other below 4. And the layout could be changed to become symmetrical and lower this inductance to around 2 nanohenry. And then, of course, the spikes are gone. And this is shown here, the 2 revisions of the board, A and B. And the customer redesigned that and improved that. And let's say, of course, at lower harmonic switching frequency, you have not so much difference. But the port on the higher frequencies, as you can see here, could be reduced significantly. And in the end, it was, something about pass or fail in the EMI test. And so this was, for the customer, really an eye-opener. That layouts where you really not think of a millimeter or so, but if you then drive at a higher switching frequency your device, you start failing. And then debugging is always the hard way. Okay, then this was basically the part on power electronics. If there are any questions, we can also do it right now or in the end.
How did you model the reverse recovery current from that? How did you model? Because the spice have an enormous problem with that. The reverse current from that is approximately the same as in the real model.
Yeah. Can you please repeat that? We have it on the recording.
I'm very interesting. How did you model in your simulation the reverse current of the diodes?
The reverse diode of the
reverse current, when the diodes turn off, there is a reverse charge which have to be emptied. So I'm very interesting because all other SPICE programs have very high issue with that, and the accuracy of this is almost zero.
Yeah, I know the problem you are mentioning. I cannot answer the question, let's say, for that particular problem, because I just know that there have been SPICE models taken from the vendor of the diodes, yeah, and implemented into the simulator and the setup. And this is SPICE net listed, and this have been SPICE models just as downloaded from the page. There have been no changes on that one. But what I can admit is that we had convergence problems. Yes, this is totally true, and this depends on such effects. On the other hand, we could solve it. Yeah, it's not that you just plug in and everything would run if you run into such leading edge problems. You have to tune the convergence settings and that kind of stuff to get it running. Yeah, and this is a significant impact on the simulation time. Yeah? So it goes up usually, and I don't know how it was solved in that particular case and how accurate it is, but our SPICE simulator is very advanced and has quite some, can be influenced by the user in different ways, so that we got it running finally. There's another question.
Okay, let me give you.
I would like to know which parasitics are simulated on the PCB level, because what I could see, you're speaking about the loops. Are you considering in the simulation also the capacitive coupling to the chassis, which would influence the common mode noise in different oscillations?
So that's the answer is this is all considered. Yes, it's a mesh which is built for an EM extraction, and the S parameters are calculated, and this contains all the couplings effects between the different physical structures, and this is considered. Of course, you have always to consider which kind of simulator you use, and this is why we have introduced PE Professional to make it easier to the user, basically to decide what to do in a particular case, and let's say the algorithm of the tool decides how to cut the design, which simulation technique or which meshing technique to apply in certain areas of the board, not that the model gets too large. But it's a 3D solution with a respective mesh, and considers all the couplings from via to via, from plane to via, and that kind of stuff. So capacitive, inductive, resistive losses. Yeah. You can even model surface roughness and that kind of stuff.
Okay, thank you.
Yeah, I just want to ask a question in relation to the same thing. Are heat sinks, for example, also modeled? And in what way? And if you have, for example, mechanical components or big components like inductors in the circuit?
We have tools where you can model 3D components, for instance, an inductor or heat sink, and you can make an EM description for this kind of structure and can bring that in as a library result. Yeah? If you want to have something like you have a very huge coil, or two coils, and you want to have the crosstalk between the coil and the board, and or the coil to the capacitor and so on, then you need to take the whole structure and make a 3D investigation here. So this would mean that you have a 3D FEM net, and we have solutions for that as well. But it's not in that. It's not in that. Here it's planar, and there is you take a model of such a huge coil or capacitor as shown, and you put it in. The first order effects, they are all okay, but there is no coupling between these models then. Otherwise, you have to generate such a coupling model before.
Is there support for thermal simulation as well?
There is support.
Thermal effects?
Yeah, I will come to that later. The answer is yes, but with respect to time, I would like to jump to the other slides, and I will come back to that. There is a support for thermal, yes. So if we look some years back, computer architecture changed. So basically, this is now meant as introduction to the high-speed 5G port in the afternoon. We have let's say, seen over the past years a dramatic change in computer architecture compared to previous years where it was more or less stable. So, and this came in by this yellow box here connecting that to accelerators. So basically, if the stuff we were using, we are talking about GPU, for instance, a graphical processor unit. And let's say the whole interfaces we have here to I/O storage and network, which is SerDes in a certain way, it came also, let's say, into play with the accelerated chips. And the key word is pooled memory. They want to share the memory here. And so what basically is coming in from server architectures in the moment is these crosslinks here between the CPU and the cores of the CPU, on-die and die-to-die communication. They are basically different in AMD, in IBM, in Intel, but they are all, how to say, very, very high speed. They are SerDes-based, they are PAM4-based, that kind of stuff. But if you extend the system more and you want to have shared memory over the usage of accelerated chips or GPUs and other stuff, basically what is coming is a cache coherent interconnect. Yeah? And this is based basically on development out of these companies playing in that role in the server architectures. And another architecture is called Gen Z, as you can see here. And just to give you a short impression, when we talk about such a cache coherent interconnect and we talk about NVLink from NVIDIA in that case, then you are here with the version 2 now out and 96 lanes, so completely about 200 gigabits per second. So it means you have a bandwidth of 300 gigabytes. And this is, of course, used in data centers, for instance. Yeah? So all what we talk about in our daily life about cloud is driving the demand for higher memory, for higher speeds, for higher bandwidth in the data centers. And let's say the external communication, they become more and more than optical. The PAM4 modulation here is a big thing to bring out the data at a respective speed. And you connect also more DDR memory here. And now the next 1-2 years, we will see DDR5, let's say, taking over the market in a maturity compared to DDR4. And here we are at speeds, for instance, at DDR5, where you need equalization techniques known from PCI Express. So this big, or say this wide digital interfaces will also use equalization techniques known from SerDes. So they will evaluate, they will train based on the channel, the tap settings to restore the data I. And this is a fundamental new approach here, basically. Here we just have seen that on the internet. I think it's from August. Here the new EPIC processor from AMD, the Ryzen, yeah, coming out. And you see here also that approach of pooled memory. It would be, of course, a bad access here from if die 0, for instance, needs to access here a memory rank over die 2, and that would cause a lot of latency. So basically it's going to the outside world and partially rerouted, or in a higher core environment looks like that. So here a lot of architecture principles are in the moment, I'm not to say changing, but expanding compared to a very strict architecture we have seen the last 5 years. Another example here, open memory interface. This is driven by IBM, and so it's for the power processors. This is then basically more for supercomputing machines, and here restricted to the P9. Yeah? And let's say here, if you look over Gen Z, you have a big advantage, because here built from Microchip, they do a memory buffer on a special core they put in to access the DDR4 memory, and by that shared pooling, basically, they get down the latency from 400 nanosecond to 80 nanosecond. And this is a big step ahead, and so you can basically, of course, spend 4 nanoseconds additional latency for the buffer itself, yeah, for the redrive of the signal, yeah, because you have here on the front side, of course, again, a SerDes architecture. And another indication that memory implementations change quite a lot in the moment. Here you see so-called standard DRAM and DIMM, but let's say redesigned in a way that there are processing units, so-called DPUs, on the DIMM itself to do additional encoding and that redrive and that kind of stuff, so you can build larger systems. This is a startup based in Grenoble, so you can look to their webpage if you're interested more. And let's say here you can build larger memory systems per channel, yeah, by spending some additional latency, and you get an additional load decoupling. Or what was just recently released as well here is, let's say from Huawei, they brought out a chip for artificial intelligence. So this is mainly targeting ADAS, yeah, so autonomous driving systems. And this has 256 teraflops and integer 8, 512 with 350 watts of design power. I mean, if you think about here at that speed, you can let's say not use standard memory anymore, and what is used here is so-called high bandwidth memory. So the architecture principle here shown, sorry too fast, shown on the right side, for that level of cache DRAM, there is the lower chip DRAM has a master who redrives the signals through the stack, so they are connected through silicon via. And this is, of course, very, very expensive, but gets you a high density and packed directly to the SoC, and therefore you can get these high performance numbers. But of course, and this comes back to the power question here, with 350 watts thermal design power, this is, of course, significantly at the density of the size of such a chip. Yeah. So you see quite some stuff going on. I mentioned already for DDR5 coming with equalization techniques. It's not so easy anymore if you implement DDR memory on your systems. Coming from DDR to DDR3, you basically had a timing budget based specification. So you have setup times, you have hold times, you have skews, and you can easily, how to say, design your layout in a respective way that you fulfill the specification for the DRAM and get your performance. Then what changed to DDR4 was basically at these data rates for DDR4, we're talking about 4 gigabits per second per pin. This was changed based on the probability distribution functions for the voltage and the timing jitter. So you have a data I specification linked to a bit error rate. And with this, you have another way of looking to your specification. You need a statistical channel simulation, because if you have a bit error rate 10 to the power of minus 15 or minus 16 specified for DDR4, you cannot simulate millions and billions of bits in a time domain simulation, because it will never end, or you have at least to wait some weeks. So you have to do statistical simulation. Yeah? And this is also, of course, possible meanwhile, and it helps you to judge your layout, what you had before, for instance, in DDR3. You can extract your parameters pretty easy. I will show later on how this works. And then you can run that simulation, and you will easily see that you cannot simply copy, paste, and change some stuff on if you're going from DDR3 to DDR4. And you cannot do that anymore if you go from DDR4 to DDR5 because of different channel effects. I mean, at that speeds with 6 gigabits here, single-ended, you have to think crosstalk and jitter are getting that high and need to be addressed also in pre-layout, so that you can do a study. How long can my channel be? Where do I put my LPDDR on the board? If I have a backside die, yeah, for a second memory rank for a higher density, do I need a separate design, or can I afford the open stub? Yeah? These are questions what you can really then answer by simulation. And let's say what we talked about here was in the DIDT arena. The physical effects in the middle are always the same, but all this stuff applies the same here basically to also the high-speed digital. Here, for instance, you see a ground flood between two differential lines, and here you have, of course, a common mode conversion, yeah, by the impedance change. You have that ground flood, which could cause you a closed data eye, basically. Yeah? And here on that particular example, on the left side, you see a bar. So this most left differential pair had really that bad data eye because it had a different impedance by that. Yeah? And coming back to the temperature question, yes, of course, you can simulate temperature if you have the layout in the board, in the tool. You can, by drag and drop, define what are your sinks, yeah? What is your power consumption. And this is, of course, a very, very difficult question if you don't have a datasheet value you can rely on. Yeah? That's a different story. But you just by drag and drop in the components, you specify their current consumption, for instance, the dissipation power, and you define your VRMs. And then you can run a DC IR drop analysis, and you can couple that with thermals. We have a library in, for instance, for heat sinks, yeah? And you can then define heat sinks for particular components with your junction to case and junction to ambient values. They are in there, pre-populated, but you might have different heat sinks, so you can also edit, of course, and then can get a temperature distribution of your device under switching conditions. You can also run a power delivery analysis, for instance, that you then go from that extend that into the AC range, so that you say, okay, at which frequency, which impedance-controlled power net do I need, and the tool has an optimizer where you can optimize your decoupling matrix, for instance. What I want to point out very shortly is if you have, for instance, a system very easily built of a controller, you have a package for that, and you have a connector, you connect another DIMM for the PCB, for instance, DRAM packages on the DIMM, and you have the DRAM I/O. Just in that simple case, for the corner cases, you have about more than 300 cases. I mean, nobody would simulate that. You do a design of experience, but you still need to know what are your worst cases. And here in the simulation is really of great help. And also you can reduce the number of cases here by a pre-layout study. So very shortly, you know that also from Altium, and it's also partially there possible. You have a stack up, you can define your stack up. You have an impedance on your line, you can easily calculate, and what we have is a 3D FEM solver for your vias, yeah? And so you can very easily set up a parameterized channel by the length of the transmission lines using your models, what you have defined from your stack up, and you can then do studies on the via interconnect, yeah? And how much stitching vias do I need, which layer do I get out, do I need a back drill or not, and you can plug these models then into a design of experiments port here. And even if you do not have models for the drivers, we offer inherent models which are specified, so you adjust your voltage swing, your rise time, your data rate, the bit sequence you want to simulate, and you can have, even without having AMI models from the vendors, you can then look at your channel, how long can it be, how many cables can I afford, because there are also cable models in, and you can configure your design target. Of course, what is also very helpful, coming close to the end, you have the possibility to have statistical distributions in. Yeah? So you can define the distribution you want to like. You can type it mathematically. You can use pre-offered distributions. And this is very, very helpful then to really see if, for instance, the case I have shown, if you have a low impedance on your motherboard and a high impedance on your daughter card, based on the specification, you might see a ringing there already when you extract the S parameters of these, yeah? And you can get a better understanding of your design space. Here you see a short example. When you read in a very complex design, it's net-based, so you drag and drop very easy the nets you want to simulate, and then the ports are assigned automatically, and the tool then gives you the TDR, TDD plots, the return loss, the transmission, and that kind of stuff where you want to look at like far end and near end crosstalk. Last but not least, one effect I want to shortly show you here. You see a motherboard layout. This is an embedded Ryzen design where you see here on the upper and on the lower the same design but with different definitions of the ports. And basically this means in DDR4 as well as in DDR3, the command address signals for the DRAM are referenced to power on the device. They are not referenced to ground. And here in that layout, the command address signals in the middle are routed to the two slots where you plug in the DIMMs. Yeah? And in that case, you just read in and you define your ports, and they are referenced to ground, but this is not according to specification. And you see here what happens. The next ground pin is far away from your signal pin. And by that port length, you get some ringing. Could resolve that better, but it's just for the principle. Some ringing in the S parameters, but if you define it for power as a reference, and the tool can handle that because S parameters only give you the delta, yeah, then you see you have very, very short ports because the device is constructed that way that the reference pin is very close to your signal pin. And in that case, you see here pretty fast that all the resonances are gone. You can extend that by including the decoupling of the board, then the S parameters change also a little bit. You can define the VDD reference as a VDD signal, include the caps and so on. And so you can really extract your channel as is. And there are really, as you see here, changes in the S parameters. And if you only get S parameters delivered and plug it into your channel simulation, you might not use the right ones. Yeah? So this is or becomes more important to have a good understanding of the quality of the model you're using. Very shortly, finishing up as lunchtime comes along, this is a short comparison between measured and simulated channel at 4.8 gigabit. So you see here, this is really, really good comparison, what you can achieve by these models. And of course, as we are a test and measurement company, very shortly, we have a lot of links from the design system itself to also the scope softwares. And all these scope softwares run standalone. You don't need to buy a scope. But what they offer are compliance applications. So there are about 40 to 50 specifications on channel operation margin according 802.11, I don't know, A to Z, yeah, and all other stuff, CIA and that kind of stuff are there. And you plug in your simulation basically as a virtual measurement, and you can use all these stuff basically for jitter analysis. Here a PAM4 example is shown, yeah, and you can directly from your simulation check your, in this case, 400 gig Ethernet, so 100 gig PAM4 split down to 56 gigabit lanes, and you can then directly test if you fulfill your specifications. Another thing here on the thermals, just want to mention, as there was the question, this is an example where you see the definition of the ports, then the current density view, and this is very important because you can also list, of course, in a table the current density per via. Because then you can find high flyers which might affect your reliability later on. Yeah? And you know, then in that range, okay, based on the temperature and the current there, I need to specify or to add some vias to relieve the situation a little bit. Yeah? So this is also possible. And yeah, that's it. This is our professional series here, basically, for instance here, power integrity and thermal the signal integrity talking about, and then the first part here was some power electronics I talked about. And there was also a question on 3D, that would be, for instance, EM, professional, and they are all under the same likelihood of ADS here, basically. So thank you very much. I'm around for discussions, for questions, of course. Thanks. I'm 5 minutes over time. I apologize. And have a good meal. Thank you very much.